Looking more of the typical questions you may get if you're trying to get into climate change communication, or even just talking at a party with Pandu Kaka. So here is the data. So the typical comment may be that the temperatures change so much from day to day and season to season. So why is this 1 degree warming since the Industrial Revolution so important? Okay, so here is the context just in terms of the Holocene. So the last glacial maximum, or the last ice age, started to end around, it reached its maximum around 21,000 years ago. Then it started to melt away because of changes in the orbital forcing again, not human made at that point. And about 10,000 years ago, we got into this agricultural way of life, and the modern human being evolved as we stand now. Of course, Industrial Revolution played a big role. So the range of Holocene temperatures, with all their civilizations and the impact on civilizations, the extinctions, the displacements, the mixing, etc., have happened within that range. So as we stand now, we have not experienced these range of temperatures. Okay, so the safe climate zone, if you want to be careful about the future, would be to assume that we are best at dealing with this range of global mean temperature change, not much more. Okay, 2 degrees centigrade warming will take us there, and business as usual would take us at 4, 5, 6 degrees centigrade. So there is the sea level rise, the extreme rainfall events, extreme heat waves, floods, droughts. For example, it's not just extreme heat waves. With the warming, the water vapor in the atmosphere goes up. So the global south that we talked about, countries like India, moist air can kill you even at low temperatures, as we saw in the previous chapters, because the body loses its ability to sweat away the heat when the humidity becomes beyond a certain threshold. So the body, when you have a heat wave or you are experiencing warm temperatures, body wants to sweat and cool your temperature. But if the atmospheric water vapor is very high, the relative change in humidity becomes so small that the body is not able to sweat at all. So those kinds of things can become deadly dangerous. Plus, we know where all the heat is, as I already said. This is the estimate of ocean heat content in the top 700 meters between 1993 and 2019. These numbers are not small. They are energy in watts per meter squared. Okay, if you consider the area of the ocean and the depth of the ocean, that is several times more than the total energy produced on the planet. So these are not tiny changes. These are massive heat changes, and specific hot spots like the Gulf of Alaska and so on are having massive perturbations of the ecosystems and so on. So think about the warming here and the Great Barrier Reef. Okay, they are dying. So those kinds of specific details. And as we said, the dynamics has to be considered as well, because you can see there is cooling here at the same time and here as well. And there are scales that have to be understood as well. This is the same data showing annual heat content from the surface to 2300 meters and from 2300 meters to more than 6.5 kilometers. Okay, so even the deep ocean is receiving excess heat now. This is not good. This is contributing, of course, to sea level rise, but it's also creating massive deoxygenation. For example, warmer temperatures cannot hold a lot of oxygen as compared to the colder waters, so oxygen is escaping from the ocean. So how do we know this carbon is really from fossil fuel burning? This we have seen several times, Charles David Keeling's curve from Mauna Loa, but now they're also being measured in the Southern Ocean, in the South Pole, and several other stations. As we said, CO2 is an inert gas, well mixed. stays around for a long time. So if you measure it in a few spots, you get a good sense of global concentrations. But there are key evidences for other things. For example, the pH of the ocean is decreasing. This is data from a different station, so Aloha seawater PCO2. So the increasing CO2 in the atmosphere is dissolving into the ocean, and it's showing up as increased partial pressure of carbon dioxide in the ocean. What happens when CO2 dissolves into the ocean? It becomes more acidic, so you can see the drop in the pH value here. Ocean has maintained the pH at around 8.1, 8.2, not uniform, for literally many tens of millions of years, because there is something called carbonate buffering system in the ocean, which we won't get into details, but if you want to explain this to people, you must make sure you understand it. Ocean moves CO2 and H2CO3 into bicarbonate and carbonate ions and adjusts the equations so that it doesn't get saturated easily and the pH doesn't change very fast. But if you increase CO2 very rapidly like we are, especially the seawater PCO2, then the reactions do not keep up, so the buffering becomes weaker and the pH begins to change. The other evidence, this is from Mauna Loa in the northern hemisphere. This is the South Pole, and this is the Cape Grim data. And we know that along with the burning of the fossil fuel, we are using up oxygen. So you can see the oxygen is dropping here. This is the change in oxygen in parts per million. Nothing to worry about. There is plenty of oxygen in the air, so we won't be suffocating anytime soon. But it is evidence that the increase in CO2 indeed comes from burning fossil fuels. But there is even stronger evidence, solid scientific evidence from the kind of CO2 that's increasing. What is this CO2? What are these fossil fuels? Basically, these are hydrocarbons from the past. When photosynthesis forms hydrocarbons, which get buried and they don't get eaten up by the microbes or other animals, and it gets converted into coal, oil, gas, and so on. Photosynthesis takes up more carbon 12 than carbon 13. So carbon has isotopes of C12, C13, and C14. We have explained it elsewhere, so we won't go into details. So if you take old carbon in a hydrocarbon, fossil fuel hydrocarbon, it has more depleted carbon in C13. So if you burn it and put it back, you're going to increase the depleted C13 in the atmosphere, which is what this is showing. See that the scale is negative and increasing down, becoming more negative. So at both Mauna Loa and the South Pole Station, we are decreasing the delta C13, which means we are producing C13 depleted CO2, which can only come from fossil fuel hydrocarbon. Okay, so another good example of answering the question of how do we know this CO2 is being emitted by us? How is it not obvious that it's coming from end of last ice age? Because we have multiple evidences, scientific evidences that are accurate and reproducible, so we can prove clearly that this CO2 is coming in fact from burning fossil fuels.